Good afternoon. This set of notes is for Algebra 2 students. We will be doing section 5.3, which is operations with radical expressions. This section of notes accompanies the 5.3 worksheet that you can download off of my Google site. All right, so the topics of radicals that we're going to be covering today are a little more complex than the review that we did in 5.1 and 5.2. We're going to be dealing with a lot more fractions and even negative exponents, which are some fun skills to learn. We're going to learn to simplify, multiply, divide, add, subtract, and rationalize fractions. Hopefully some of this looks familiar, that it's not all completely new. If it is, you might want to watch this video more than once to make sure that you've learned everything you need to know. Okay, Roman numeral 1, we're going to start with advanced simplifying. So basically doing what we were doing before, but with slightly more complex problems. First thing you need to know is when you simplify radicals, the order of operations still apply. So you will start on the inside of the radical and work your way to the outside. Remember that the radical bar itself is a grouping symbol, so inside the grouping symbol first. All right, for fractions, we have a theorem that says that if you have a fraction, let's say just a over b with a root k, you are allowed to split that fraction into top and bottom. So the kth root of a can go on the top, the kth root of b can go on the bottom. And this goes both ways. You can combine radicals or you can split them apart, as long as if you start with two separate, as long as the roots are the same, this is possible. Remember what these theorems are called from geometry. When it goes both directions, it's called biconditional, because it goes both directions. And again, the trick to using this correctly is that the roots must match. All right, so we're going to practice that in a moment. The second concept related to simplifying radicals in fractions is the concept of rationalizing. When you rationalize a fraction, the basic idea is that you are going to remove all radical bars from the denominator. We don't mind them in the numerator, but we can't end a problem with a radical bar in the bottom of the fraction. So let's do an example of this. We're going to do the fourth root of 32 over 2x to the fourth. Now, one of the questions I often get is, can I go ahead and divide 32 by 2? The answer is yes. You can reduce the inside fraction just like you would normally before starting the process of rationalizing. So we're going to do that. 2 goes into 32 16 times. So now we have the fourth root of 16 over x to the fourth, which is a little simpler. Using our theorem, we can split this into the top, which is the fourth root of 16, and the bottom, which is the fourth root of x to the fourth, and then simplify each of them separately. So starting at the top, we're going to prime factor the 16. 16 is 4 times 4, so 2 times 2 for the first 4, 2 times 2 for the second 4. Because there are 4 2's, and this is a fourth root, 1 can come out. There is no radical left on the top. Now the bottom. When you have x to the power of 4, it means you have 4 x's being multiplied together. Because there are 4 x's, and this is a root 4, 1 x comes out, and because this is an even root, remember that we don't know if the original x was positive or negative, because when you raise it to an even power, like 4, the negative goes away. So we're going to use absolute value bars around the x to show that it might be positive or it might be negative. And that would be your answer. Let's do another one that's a little more challenging. So example 2, this is going to be the 5th root. So we'll get into an odd root. 5th root of 32, a to the 5th, b to the negative 1, over 243, b to the 5th. Okay, so remember that we want to simplify from the inside out. So first thing you want to do is move that b value. We can't really do very many operations with a negative exponent. A negative exponent means that that b isn't actually in the top of the fraction, it's in the bottom. So we move it to the bottom where it gets combined with the other b's that are down there. So instead of having b to the 5th, when we move this 1b down, we have b to the 6th now at the bottom. And then we have 32, a to the 5th left on the top. Okay, so now we're going to use our theorem, and we're going to split the radical into separate top and bottom so that we can simplify them. So on the top, it's the 5th root of, well, 32 is 8 times 4, so 222 for the 8, 22 for the 4, and then I have 5 a's, 1, 2, 3, 4, 5. Now on your actual problems, if you have 5 a's and it's a 5th root, you are welcome to simplify the a out without actually writing out all 5. But this is notes, so we want to write things in the most explicit way possible. On the bottom, we have another radical, 5th root, and 243 ends up being 27 times 9. So 3 times 3 times 3 is the 27, times 3 times 3 for the 9. And then we have 6 b's. 1, 2, 3, 4, 5, 6. Now that we have factored the top and the bottom, we are ready to start simplifying things out of the radical. On the top, I have 1, 2, 3, 4, 5 2's. 1 comes out. For the a's, I have 1, 2, 3, 4, 5 a's. 1 comes out. This is an odd index, so we do not have 2 answers for a, just the 1. So on the top, we actually don't have any radical left. Now let's do the bottom. I have 1, 2, 3, 4, 5 3's. 1 comes out. Now I have 6 b's, so I'm going to take out 5 of them. 1 comes out. And I'm going to have a b left inside of the 5th root. So far, we've been basically just simplifying. Exercise 1, we didn't need to rationalize the bottom because there was no radical left. Number 2, we do have a radical in the bottom of the fraction, so we will need to rationalize that. So the way you rationalize is you're going to multiply the bottom by the 5th root of the number of b's that you would need to take the b out. Well, I've got 1. It's a 5th root. I need 4 more. So I'm going to multiply it by the 5th root of b to the 4th. Now, as always, when you do it to the bottom, you have to do the exact same thing to the top. So the 5th root of b to the 4th is multiplied by the top. So on the bottom, when you combine the 5th roots, you have 4 b's plus 1 is 5. So 5 b's, 1 comes out. So now I've got the original 3b times another b that came out. And there's no radical left on the bottom. That means this is rationalized. On the top, everything just gets stacked up. 2a times the 5th root of b to the 4th. Last thing, if are there any scalars top and bottom that will divide out or need to be multiplied together? So this bottom will need to be multiplied. I get 3b squared. And the 2a and the 3b squared don't have any factors in common, so we leave them as is. So your answer is 2a, the fifth root of b to the fourth, over 3b squared. This is rationalizing, removing the radical from the bottom. You multiply by what you need to clear out that radical. So if this had been a sixth root, I would have needed a b to the fifth, because 5 plus 1 is 6. So you always multiply by what you need so that the radical goes away. All right, Roman numeral 2, adding and subtracting. Okay, for adding and subtracting, there are some rules of the process. First of all, when you are adding or subtracting radicals, it's basically the same technique as collecting like terms, where you add x's to x's, y's to y's. The biggest difference is when it comes to radicals, you have to be really careful that both terms have the same root. And they also have to have the same radicand. So this is a very picky process. They have to have the same root and the same radicand. Let me show you what this looks like in comparison to collecting like terms, which you're already very good at. So for collecting like terms, you might take something like x plus 2x plus y, and you know by practice that only x's can be added together because the x's match. So 1 plus 2 is 3x. You are not able to add the y, so the two stay separate. So let's look at the same problem now, but with radicals in it. So instead of x, we're going to have square root of x plus 2 square root of x plus the square root of y. It's the exact same thinking. Radical x and radical x mean that these two can be added together. There is an invisible 1 in front of the radical x, just like there's an invisible 1 in front of that lonely x up here. So 1 plus 2 is 3 radical x, and it stays radical x, and plus the radical y, which stays separate. If you have a square root x and you're trying to add it to a cube root x, that simply is not possible. The radicands do match, but because the first term has an invisible 2 as the root, the roots don't match. So because 2 and 3 are not equal to each other, if you were asked to simplify this, you would just rewrite it. Square root x plus cube root x. And that would be your answer, because there's nothing you can do as far as addition goes. All right, those are the basics of adding and subtracting. Let's do some examples of this. All right, example 1. Cube root x plus square root x plus cube root x squared. Now, looking carefully at this, the first two do have the same radicand, but one is an index of 3, the other one is an index of 2, so you can't add them. The first and third terms both have a root 3, but the radicands don't match. So in this particular problem, you can't add anything at all. It has to stay separate. Again, because between these two, the roots are not the same. And then between the first and the third, the radicands are not the same. So nothing can be actually added. It's a very picky process. Example 2. 3 square root 28 plus 5 square root 7. Now, at first look, it doesn't seem like these can be added. They are both a root 2, but 28 and 7 are not equal. Keep in mind, though, if you can simplify, you need to do that first. before you attempt to decide whether it is able to be added. So for 28, that's 4 times 7, so 227. 2 2's, 1 comes to the front. So now I have 6 radical 7 plus 5 radical 7. 5 radical 7 is already simplified. Now the roots match and the radicands match, so you can add these together. 6 plus 5 is 11 radical 7. That would be your answer. All right, going a little more complex. Example 3. In all of these, the scalars could be added. A 5 plus a 6 is able to be put together. What do you do, though, if it's not possible to add the scalars? So here's our example. 2 cube root of 3r plus 4x cube root of 3r. Now, both of them are cube root. Both of them have a radicand of 3r, so you can add them. The problem is what to do with the 2 and the 4x. I can't add an x to a 2. So the answer is you put them in parentheses and leave them separate. And then tag on 1 cube root of 3r. Of course, you want 4x to come first in your answer. So 4x plus 2 quantity cube root of 3r. And that would be your answer. You can't get it any simpler than that because you can't add an x to a number term. All right, last problem of the notes, and then we're done. Example 4. Let's say you've got 8 square root of 12x cubed plus 3 square root of 75x cubed. So at first look, they are both square roots, so that's good, but the radicands are different. However, there's some simplifying that can happen on this. So we're going to simplify both and revisit it. So here we go. Factoring 12. 12 is 4 times 3, or 223, and then it has 3 x's, x, x, x. For the second one, we have a 3 out front for the scalar. 75 is 25 times 3. So 5, 5, 3, and then x's, x, x, and x. All right, back to our first one. It's a square root, so 2 2's, 1 comes out and gets multiplied by the other 8. 2 x's, 1 comes out, and because this is an even root, the x gets your absolute value bars. On the second one, 2 5's, 1 comes out. 2 x's, 1 comes out, it gets absolute value bars. So remultiplying together, I have a 16 absolute value x square root 3x plus 5 times 3 is 15 absolute value x square root 3x. Now that they're simplified, the roots match and the radicands match, and the scalars can be added. They both have an absolute value x. So 16 plus 15 is 31, absolute value x, square root of 3x. And we are done. I hope you found this helpful. Remember that the worksheet for 5.3 is on my Google site, so be sure to download it. And it does have some answers to the odds so that you can check your work.